All right, so today's lesson is cycles of matter, but specifically today we are looking at the carbon cycle, nitrogen cycle, the phosphorus and the sulfur cycle as well. So recall that matter on Earth is finite. So the matter we're talking about is carbon, oxygen, nitrogen, and phosphorus. Because it's finite, it's getting continuously recycled in these biogeochemical cycles. And these basic building blocks for life, they're going to move through the living and the non-living components of the ecosystem. If the cycles get disrupted, the balance of the ecosystem is also disrupted. So let's take a look here at nutrient cycling. So recall that when we talk about matter, the biosphere is a closed system because everything just gets recycled on Earth. When we talk about energy, the biosphere is an open system because we are getting the energy from the sun, and some of that energy also gets reflected back into space. So some nutrients are not replenished in the biosphere. They are finite and they cycle through the biosphere. And these are the biogeochemical cycles. And these are the pathways through which all nutrients cycle. So there's going to be both a slow and rapid cycling. So when nutrients move quickly between organisms or abiotic components, that is called rapid cycling. For example, photosynthesis and cellular respiration, they are rapid cycles. When nutrients become unavailable for a long period of time, so for example, if the nutrients are deep in the ocean or they're deposited in rocks, then it's part of the slow cycling. Here in this diagram, the dark green lines are showing the movement of nutrients, and the dashed lines are showing the movement of energy. So nutrients are not depleted, but energy does get depleted. So we need a constant supply of solar radiation to sustain the biosphere. So again, rapid cycling is when substances cycle between nutrient reservoirs quickly. Carbon can move, for example, from producer to consumer to decomposer and then back into the atmosphere. That would be rapid cycling. Slow cycling, substances accumulate and become unavailable to organisms. So for example, fossil fuel deposits like coal and oil, they are carbon reservoirs formed over millions of years as organic matter built up without fully decomposing. So it can take millions of years for these kind of substances to again become available as nutrients for living organisms. And then that is an example of slow cycling. This is just a diagram showing how nutrients are cycled between biotic and abiotic components, if they're available as nutrients or if they become unavailable. So for example here, coal and oil, which are like fossil fuels, they can become unavailable. But we can use the fossil fuels when we are extracting them from ecosystems. Burning of fossil fuels, those would be like abiotic components available as nutrients and so on. So we're going to focus on the carbon cycle. Carbon makes up 20% of the human body. It's important in making up the carbohydrates, the fats, the proteins, hormones, and vitamins. Life on Earth is carbon-based, so all living organisms have carbon in them, and it's because it provides the framework to all molecules. Oxygen is the most common element found in the human body. It's important in carbohydrates, fats, proteins, hormones, and vitamins. And then lastly, phosphorus, nitrogen, and sulfur. They are found in proteins and they're found in vitamins. And then nitrogen is also important in the building block of DNA. All right, so this first diagram is showing the carbon and oxygen cycle. So we can start, for example, oxygen in the atmosphere. It's being released by plants and trees. It gets used in the burning of fossil fuels and wood. It's used in cellular respiration and then taken in by decomposers, taken in by consumers. Here it's showing high-level consumers as well as primary consumers. All right, so we need oxygen to survive. And then carbon dioxide is taken in by plants, trees, it's taken in for photosynthesis. But notice here, there's also an excess of carbon dioxide coming from the burning of fossil fuels. And then we release carbon dioxide into the atmosphere when, for example, when we exhale. So that's what's showing here. And carbon is also released into the soil, for example, and it is used by decomposers. So photosynthesis, again, produces oxygen gas, which is needed for cellular respiration. And so we see the top half of this is showing photosynthesis, and then the bottom half is showing cellular respiration. What we're seeing here is that the overall equations for both photosynthesis and cellular respiration are complementary. And they both contribute to that rapid cycling of carbon and oxygen. All right, here is just another diagram. This is just showing carbon dioxide. So again here, burning of fossil fuels is going to release carbon, human and animal respiration, plant respiration, deforestation, there's going to be a buildup of atmospheric carbon dioxide. It does get used up in during photosynthesis, also gets stored in large land plants, and then any organic matter such as waste and dead animals, for example, they'll contribute to the soil. More carbon enters the soil by that organic matter. As well here, we can see in the aquatic cycling here, there's photosynthesis and respiration occurring there as well. And fossil carbon, fossil fuels lock carbon out of the carbon cycle. All right, carbon cycle. There's also these areas called carbon sinks. So when we talk about carbon sinks, they are the reservoirs of carbon. So for example, boreal forest ecosystems are significant carbon sinks because of the trees and because of peat. So peat in bogs in Alberta are also called muskeg, and some peat bogs in Siberia are like 10,000 years old and are among the world's top carbon sinks. If these peat bogs are drained and decomposition is allowed to occur, then that carbon that is stored will get released as carbon dioxide. Then, instead of being a carbon sink, these ecosystems will now become a source of carbon. Trees in forests, they act as carbon sink because they absorb more carbon dioxide than they emit into the environment. So basically, trees, they store large amounts of carbon, and most of it only usually gets released when they die and decompose or are combusted by forest fires. Quickly here is just the oxygen cycle. Like we saw before, carbon and oxygen cycle are closely related because how we saw in photosynthesis and cellular respiration, they're the main processes responsible for the balance of oxygen and carbon dioxide. So on the left diagram, you see that relationship between oxygen and carbon dioxide. So CO2 comprises about 0.03% of the atmosphere. Oxygen is about 21%, and it's a relatively small part of the total oxygen system. The oxygen system, as we will see, also involves the cycling of other nutrients like sulfur, phosphorus, and nitrogen. Okay, so next we're going to talk about the nitrogen cycle. So nitrogen gas, which is N2, that is the chemical formula for nitrogen gas. It makes up about 78% of the Earth's atmosphere. And it's an essential part of proteins in organisms, and it's also found in the DNA in cells. But most organisms can't use that atmospheric nitrogen. But there are some bacteria that can convert that atmospheric nitrogen and convert it into ammonium, NH4+, and they do that by nitrogen fixation. So for example, in here we're looking at nitrogen fixing bacteria found in the nodules on the roots of some legume plants. And so basically those lumpy nodules in legume plants, they contain nitrogen fixing bacteria, and they can take the nitrogen and in the atmosphere and convert it into ammonium. Then it can be then shared with plants, and the plants provide bacteria with the sugars produced in photosynthesis. So it's like a mutualistic relationship. Lightning's another method. Lightning can convert atmospheric molecular nitrogen to nitrate, which is a form of nitrogen that plants can use. So ammonification is ammonium when ammonium is produced when decomposers break down organic matter, and then soil bacteria convert the ammonium into either nitrite, which is NO2-, and then into nitrate, which is NO3-. Plants can then use the nitrates as a nitrogen source. And then denitrification is when denitrifying bacteria, they can complete the cycle by converting the nitrite or the nitrate back into the nitrogen gas. And this can occur in environments with little oxygen. All right, so here is a diagram showing the nitrogen cycle. You've got the nitrogen in the atmosphere, and then you'll have nitrogen fixation happening. That nitrogen fixing bacteria in the nodules and soil can convert it into ammonium. Then the nitrifying bacteria can convert it into nitrite or nitrate, which can then be used by plants. To complete the cycle, you have denitrifying bacteria, which is going to convert those back into atmospheric nitrogen. And that's happening in the aquatic ecosystem as well. All right, so this diagram here is just showing the nitrogen cycle and how the legumes are an important part of the nitrogen cycle because they contain that nitrogen fixing bacteria in their nodules. Another thing here is if you've heard of crop rotation in farming, this is when farmers rotate their crops over the years so that different crops are being planted over the years, and this is necessary to maintain high levels of nitrogen in the soil. Farmers will plant a legume in their soil once every few years to increase the nitrogen level in the soil without having to use fertilizer. All right, so just in summary, again, there's about 78% of nitrogen in the atmosphere, but organisms can't obtain the nitrogen from the air. We have to use these nitrogen fixing bacteria because they are able to convert that nitrogen gas into a form that can be used by plants and animals. So nitrogen gas, again, is in that elemental form, which is N2 right here. And then animals obtain nitrogen from protein in plants, and plants uptake nitrogen as the nitrate ion or the nitrite ion, so NO3 minus or NO2 minus. For nitrogen gas to be used by plants, the gas has to be converted by certain types of bacteria into ammonia by that process called nitrogen fixation. The bacteria that perform nitrogen fixation are found in those nodules of roots of plants called legumes. And then other types of bacteria, which are the nitrifying bacteria, they can convert the ammonia into nitrates and nitrites by a process called nitrification. So pause here. All right, so next we are talking about the phosphorus cycle. So phosphorus, again, it's part of the DNA. It's also important in ATP because it's an energy carrier, and it's a major component of bones and teeth. But phosphorus, it doesn't recycle through the atmosphere like we saw previously with nitrogen, carbon dioxide, and oxygen. Phosphorus is found in soil and water, and weathering will gradually release the phosphorus trapped in rocks. So animals obtain phosphorus by consuming foods such as milk, grain, and meat. Producers like plants and algae can only use phosphorus if it's in the form of phosphate, which is PO4 3-. So the scarcity of phosphorus keeps the growth of producers in balance, but it can also limit the growth of crops. So that's where like fertilizers come in. So here we're seeing an algal bloom. This is when there's a growth of algae in aquatic ecosystems. And it's usually limited by the amount of available nutrients. But there's an overgrowth of algae, which is called an algal bloom. And it's usually because of excess phosphorus being released into the environments because of, for example, detergents, or for example, fertilizers and so on. So overgrowth of algae is going to produce a large amount of organic matter, and then when decomposers break down that organic matter, they use up the oxygen in the water, and then therefore there's more death. There's death of fish and other aquatic life, and it just continues. And it just worsens. So here, this is near Ontario. It's in 1973. One side of the lake is bright green because of the algal bloom, because of excess phosphorus. All right, so again, phosphorus, it doesn't cycle through the atmosphere. Phosphorus in the biosphere is stored in water and geological formations, for example, like rocks. It's released from sediments and rocks and into the water, for example, by weathering, and then it becomes available to plants in the form of that phosphate ion. And then here on the right-hand side, we are seeing when there's a buildup of nutrients. It's called eutrophication in aquatic ecosystems. And for example, nitrates and phosphates from fertilizers and from household chemicals, they can cause eutrophication in bodies of water. It's excess nutrients. It's going to support the overgrowth of algae, which goes into the algal bloom that we just talked about. All right, and then we have the sulfur cycle. Lastly, it's an important part of proteins and vitamins. Plants and algae use sulfur in the form of sulfate, SO4 2-, which dissolves in water. And then decomposers return most of or much of the sulfur to soil or to the atmosphere. So you've probably smelled sometimes that sulfurous smell in a muddy pond or wetland. That is hydrogen sulfide, H2S. Acid deposition. So fossil fuel deposits like from oil, coal, and natural gas, they contain sulfur. And then weathering will release some sulfur trapped in rocks. Volcanic activity also releases sulfur into the atmosphere as sulfur dioxide. Sulfur dioxide, however, it reacts with oxygen and water vapor in the atmosphere to form sulfuric acid, H2SO3, and sulfuric acid, H2SO4. And this results in acid deposition, such as acid rain, acid snow, acid sleet. And large amounts of this acid deposition can damage plants, it can acidify lakes, and it can leach nutrients from the soil. When we burn fossil fuels, it's also releasing sulfur into the atmosphere, which contributes to more of that sulfuric acid and sulfuric acid. All right, so here is the sulfur cycle. So again, notice here on the left, we have the burning of fossil fuels, any volcanic activity, mining and fossil fuel burning. There's an increase of sulfates or sulfur dioxide in the atmosphere, which can lead to sulfuric acid and sulfuric acid, which contributes to acid precipitation. So sulfur compounds, they don't stay in the atmosphere long. When there's rain or snow, sulfur is returned to the Earth's surface, and it eventually gets used by plants, algae, and bacteria. And the decomposition of organic matter, and including volcanic activity and human activities, they distribute sulfur into the air, soil, and water. All right, so I'm going to pause here